Section 15.8, Stokes' theorem. So this is going to be like Green's theorem, just in a third dimension, in a higher dimension. So let's just jump right on into the theorem itself. Okay, so I'll just give it to you here. Let S be an oriented surface with a unit normal vector n, bounded by a piecewise smooth simple curve, bounded by a piecewise, PW piecewise smooth closed curve C, with a positive orientation. Okay, and remember in 2 dimensions that was just counterclockwise. Same idea. We're still, so if you took a projection of this surface onto the xy plane, we'd still be going around it in that counterclockwise direction. Okay. Then if F is a vector field whose components have continuous first partial derivatives, on an open region containing S and C, then, okay, the line integral of f dotted with dr, so the curl, right? Well, let me just write this down, is equal to the double integral of s times the curl of f dotted with n ds. Okay, so just to remind us, the curl of f, I don't know why I keep losing that last letter of these words. The curl of f is equal to the dot product, cross product. The divergence is the dot product, dd, divergence dot product. Curl is the cross product, curl cross product. Okay, so the curl of f is equal to, that was the cross product of the derivative operator, the partial operator, and f. So it's equal to I, j, k of the partial with respect to x, of the partial with respect to y, of the partial with respect to z, of m, cross with m, n, and p, right? Okay, and then the normal vector, if it's oriented upward, is going to be equal to negative g sub x of xy minus, in the I direction, minus g sub y of xy in the j direction, plus k in the z direction, plus k, yes, in the k direction, plus 1 in the k direction, guys. Okay, so there's that. Now remember, because it's a plus 1k, that's going to be oriented upwards. All right, and then we would dot these together to get the integrand for our Stokes' theorem formula. Okay, so let's go ahead and do an example where we are going to use Stokes' theorem. So let's do some setup. So we're going to let C be the oriented triangle lying in the plane. 2x plus 2y plus z is equal to 6. Okay, so let's give a quick sketch of that. So if z is 0, we've got x plus y is 3. So it's going to have x and y intercept 3. If x and y are both 0, z is equal to 6. Okay. Okay, so this was x plus y equal to 3. This is where in the xy trace, this is, I'm sorry, the zy trace, x, y, z. So in the yz plane, that line there is going to be given by 2y plus z equal to 6. So z is equal to 6 minus 2y. And here it's z is equal to 6 minus 2x because y will be equal to 0. Okay, so we've got that. Our region is the projection into the xy plane. And we do have a normal vector that will be coming straight out of this, so that's our normal vector. All right. Okay, so then we are then asked to evaluate the line integral of f dotted with dr, where f of xyz is equal to negative y squared I plus zj plus xk. Okay, so according to Stokes' theorem, this line integral is equal to the integral over the surface of the curl of f dotted with the normal vector ds. Okay, so we're going to first have to find the curl, then find that normal vector. So the curl of f, that's the determinant of ijk, partial with respect to x, partial with respect to y, partial with respect to z of m, n, and p. Okay, so that's going to be equal to ij, oops, gotta get the j in there first, ijk of, okay, our partials should be partial with respect to y. There we go. Of, okay, so m is negative y squared, z, n is z, and p is just x. Okay, so that's going to give us the following vector. Partial with respect to y of x is 0, minus the partial with respect to z of z is 1, minus the partial with respect to x of x is 1, minus the partial of z with respect to negative y squared is 0. And then the partial with respect to x of z is 0, minus the partial with respect to y of negative y squared is negative 2y, so minus a negative becomes positive. So that's going to be negative 1 in the I direction, negative 1 in the j direction, and 2y in the k direction. Now, that normal vector, to find the normal vector, we first need to know what is g. Well, we were given our plane here, so z, get another color, z is g of x, y, okay? So then g with respect to x, the partial of g with respect to x is going to be, you know what, let's go ahead and solve this for g. So this is 6 minus 2x minus 2y, there we go. So that's going to be negative 2, and then the partial with respect to y is also negative 2. So then our normal vector is going to be negative 2, negative 2, and then 1. It's oriented upwards, so it's 1 in the k direction. Okay, so now we dot these together. So the curl of f dotted with n, that's going to be negative 1 times negative 2 plus negative 1 times negative 2 plus 2y times 1. So that's equal to 2 plus 2 is 4 plus 2y. But I just realized I made a mistake. Did anyone catch my mistake? It's right here. Remember, the normal is the opposite of gx, opposite of gy, 1 in the k direction. Right? I did not negate these, so that was my bad. I need to fix that. So this actually should be equal to negative negative 2, so positive 2, negative negative 2, positive 2, and then 1. Okay, so this should be positive 2, positive 2, positive 1. So I do apologize for that. But that's going to turn this into a negative 4 plus 2y. So there's my curl dotted with the normal vector, negative 4 plus 2y. That's an easy mistake to make, especially when your partials are already negative. Our brains see that. It's like, oh, it's already negative. We don't have to worry about it, but we have to be very, very careful in our logical steps. Okay, so negative 4 plus 2y is our integrand. So then setting up our integrand, what we have is our integral over s of negative 4 plus 2y ds. So let's go back up here and take a look at our region and see how we can look at this, how we can get this bounded. So I'm going to redraw our region in the the xy plane. XY plane. Okay, so it's intercepting both axes at 3. Okay, and this is x plus y equal to 3. So we can choose to integrate this with respect to y first or with respect to x first. It does not matter, however we choose to define it. I'm going to go ahead and do it with y first. So our lower boundary for this region is y equal to 0, and our upper boundary for this region is going to be y equal to 3 minus x. Then our boundaries on x are just going to be 0 to 3. Okay, so let's go ahead and put this into our integral. So this is going to be equal to the integral from 0 to 3 of the integral from 0 to 3 minus x of negative 4 plus 2y dy dx. Integrating this gives us our integral from 0 to 3 of negative 4y plus y squared, evaluated from 0 to 3 minus x dx. Plugging in 3 minus x, we get negative 4 times 3 minus x is negative 12 plus 4x. Plus y squared, if I put in 3 minus x, I get 9 minus 6x plus x squared. Putting in 0, we get 0, 0, so we subtract 0 there. You can't ever just assume that, folks. It's a very common error, but if there's an e to the x in there, or if there's a constant in there, it doesn't evaluate to 0. It's something we have to watch out for. Okay, so then this is the integral from 0 to 3 of, combining like terms, we get negative 3 minus 2x plus x squared dx. So that's, if we integrate that, we get negative 3x minus x squared plus 1/3 x cubed, evaluated from 0 to 3. Plugging this in, we get negative 9 minus 9 plus 1/3 times 27, which is going to be 9, minus, putting in 0, we get 0 all across the board, so that's equal to negative 9. And there we have it. Okay, so there are plenty more examples out there, some really good videos I highly recommend you look up on Stokes' theorem if you would like a deeper understanding of this theorem, but I think for our purposes, being able to apply it in this way is what you really need. Now there is one last thing, a gift from our author at the end of section 15.8, a summary of integration formulas. So I'm going to go ahead and write those down. They're very handy and it's good to have them. So let's go ahead and get them down here, and that'll be the end of Calculus 3, you guys. We made it to the end. Okay, so let's write these down. Summary of integration formulas. And if you are interested, you can look this up in your book. It is on page 1122. Okay. First one's the fundamental theorem of calculus. Okay, the fundamental theorem of calculus, this is something you should definitely know. It is the integral from a to b of f prime of x dx is simply f of b minus f of a, right? Okay, so the fundamental theorem of calculus. The fundamental theorem of line integrals. Okay, so we saw this one a few sections ago. This one is the integral over c of f dotted dr. That is equal to the integral over c of the gradient of the potential function f dotted dr, okay, which is equal to f of x of b minus f of b, y of b, minus f of x of a, y of a. Okay, so it's really just the fundamental theorem of calculus, just extended a little bit. Then Green's theorem. Okay, so this one says if we have the integral over c of m dx plus n dy, that's supposed to be a plus sign, there we go, plus n dy, that this is equal to the double integral over r of the partial of n with respect to x minus the partial of m with respect to y dA, which is equal to the partial, the integral over c of f dotted with t ds, which is equal to the integral over c of f dotted with dr, which is equal to the double integral over r of the curl of f dotted with k dA. Okay, that was exciting. Lots of equivalence there, right? Okay, but we're We're not quite done yet, right? Because we also had the flux going on. So we have the integral over c of f dotted within ds, that was equal to the double integral over r of the divergence of f integrated over the area. Okay, so all of that came out of Green's theorem. Then we have the divergence theorem. It said that the double integral over s of f dotted within ds was equal to the triple integral over the solid region Q of the divergence of f dotted within. Oh, I'm sorry. I just jumped ship and grabbed the wrong thing. That is incorrect. It's just the divergence of f. There we go. The divergence of f dv. Looked back up at the previous part there. Okay, and then finally, Stokes's theorem. It's Stokes's. So Stokes's, there we go, Stokes's theorem, which says the integral over c of f dotted with dr is equal to the integral over s of the curl of f dotted within ds. There it is. So there are all of our theorems from this section. All of our integrals from this section, this chapter 15, in one nice, tidy little place, so that you've got it. You've got everything you need. And this is the end. This is it. This is the end of chapter 15, you guys. We made it all the way to the end of the book. If you have any questions about any of this, please let me know. As always, there are some really, really good resources online. Highly recommend Paul's online notes for this chapter. Highly recommend some of the Khan Academy videos. There are other videos out there as well. There are good examples that you can watch. All kinds of great stuff. But if you have any questions at all, please let me know. Take care, everybody.